Hi everyone, my name is Abdulkadir Tural from Physics Department. Today I am going to present my Physics 212 Modern Physics term project, which is on relationship between the temperature and the forward voltage of a laser diode. In the early days, basic components like insulators and conductors were enough for building electronic devices such as transmitters and receivers. However, as electronic devices became more complex, scientists and engineers needed to develop more advanced circuits. Semiconductors became essential because they provide more efficient and effective solutions. Without semiconductors, resistors would cause significant energy waste and they take up less space, making them ideal for complex systems. Semiconductors have become one of the most researched topics in physics. Early studies by scientists like William Shockley and Ferdinand Braun in the late 1800s found that some conductive materials didn't behave like metals. Classical models like the Paul-Drude model and the Wiedemann-Franz law couldn't fully explain semiconductors. It wasn't until the mid-20th century that key quantum mechanical theories, such as band theory and the effective mass model, provided a better understanding. Today, semiconductor research aims to design materials for various applications, considering different conditions like temperature, pressure, and humidity. For example, as temperature increases, a diode's forward voltage decreases. In theory, we will look at the relationship between a laser diode's forward voltage and temperature. The band gap is the primary cause of forward voltage, which is affected greatly by temperature of the electrons. We will employ an empirical model to examine the validity of our experimental data because a variety of factors can alter a laser diode's band gap. We can approximate the result rather accurately thanks to Varshni's equation, which is expressed as the below equation. And as seen from the figure, the band gap energy of semiconductors tends to decrease with increasing temperature. When temperature increases, the amplitude of atomic vibrations increase, leading to larger interatomic spacing. And coming to computational results of the experiment, we use the co- we use Python codes for the computational part of the experiment. In this project, we use Python's Qtip library to study how energy levels in a material change. First, we set up the energy and the interaction values for the material, as shown in the left blue smooth lines. We used a method that accounts for how atoms in the material interact with their neighbors. This method helped us build a matrix that represents these interactions. Then, we solved this matrix to find the energy levels. You can see the right hand side, the numerical solution for the eigenvalues of matrix. And finally, we plotted these energy levels for specific values to understand the material's behavior. From this figure, it is evident that the numerical solution closely aligns with the theoretical solution of the dispersion relation, providing a reliable estimate. And equipments and the circuitry. In the phase 1, the first part of the experiment, we use these basic circuit which consists jumper cables, breadboard, a resistor 33 ohm and 56 ohms, and a Peltier cooler and a thermocouple. Uh, and then for the phase 2, we additionally use external battery because we couldn't do it in the EE lab. So we we use dry ice for the extremely low temperatures. The same experimental setup was set up with dry ice, and the experiment was repeated with 6.4 voltage drawn from an external source. Changes in forward voltage were observed after waiting long enough for the laser diode to cool down. And initially, we obtained the 4.39 volts as forward voltage of the laser diode. When we wait long enough, uh, our peak value is 4.48 volts for the forward voltage of the laser diode. And here you can see the different results at different times, and our experimental results. We plot the graphs, and our first result in phase one, um, we use Peltier circuit, and we use this circuit in the room temperature, around the room temperature, between 10 degrees Celsius to 45 and 50 degrees Celsius. This is the fitted line, uh, and our this black dots are our set of data, and our final graph will look like this. And this, the very left side of the graph, are 4.48 volt forward voltage at the approximate minus 70 degrees Celsius. We assumed that way because we couldn't measure the exact temperature at a given long wait time. To conclude, in this project, we explored how temperature affects the forward voltage of a diode using the tight binding model and band gap structure. For safety, we avoided using dry ice indoors and ensured we didn't touch it with bare skin. Measurement errors mainly came from the sensitivity of our equipment and environmental factors. Heating the diode above 10 degrees Celsius and extensive use of circuit equipments also caused deviations. Our key finding is that temperature directly impacts the band gap, which in turn changes the forward voltage of the semiconductor laser diode. Thanks for listening.